Okay, so the question is saying that using Euler's method showed that the acceleration components of a two-dimensional fluid flow are given by this: the first component along the x, the second component along the y, and hence, given that they were given a this is a velocity vector, determine the acceleration vector at any point x, y at any time t. So when you're describing the fluid motion using Euler's method, okay, using Euler's method, the velocity components are given by a function, let's say f1 of x, y, and t. Remember, this is a two-dimensional flow. That's why we have one x and y. This is the velocity along the x, and the velocity, other velocity component along the y will be given by f2, x, y, and t. So now you have to find the difference equation, the total differential equation for this velocity component and for the other velocity component. Because remember, acceleration is the rate of change over velocity. It could be with respect to time or space. So now the total differential function for this first component is given by du being equal to we're going to differentiate the same function with respect to the first space coordinate here, x. Then we write dx plus, again differentiate with respect to y, and write dy plus, differentiate with respect to time, and then write dt. So when you reach that point, you then now divide through by dt. Divide through this equation by dt. So you're going to have du over dt be equal to partial differential derivative of this dx over dt plus u y dy over dt plus u t dt over dt. And then we're going to write this dx dt dy dt in front of the partial derivatives here. Before we do that, let's do that. We're going to have du dt be equal to dx over dt, partial derivative of this with respect to x, okay, then plus dy over dt, partial derivative of this with respect to y, plus dt over dt is simply 1, so you remain with dt there. But note that, note that acceleration is equal to the change in velocity, change in time. Okay, this is the acceleration along the acceleration is given by this formula. We can also find the acceleration sorry the velocity can also be described along the x-axis by the change in the x with respect to time. Also, acceleration along the y-axis can be found by the change in the y with respect to time. So we can substitute now these, okay, in this equation. So substituting these there, we're going to have the acceleration along remember this is the velocity along the x-axis. So acceleration along the x-axis with respect to along the x-axis will be given by this dx dt is u, the partial derivative plus this dy dt is v. So v, differentiate now this with respect to y, plus this will be just the derivative, partial derivative of u with respect to t. And this is the first component, the acceleration component that we found. So similarly, but you are supposed to finish it. Ay can be calculated and it can be found to be u v x plus v v y plus v t in a similar way.